All right, so now let's talk about the extension of surface tension to situations where the liquid is also in contact with a solid. So that's generally called capillaries or capillarity. So capillaries are basically tiny tubes or any passage, really, a pore, could be a pore, where surface tension is strong enough to pull in or even push out, in some cases, the fluid that you're interested in. So if you have a situation where liquid is in contact with a solid and air, or any other gas really, if you zoom in really close to where the three of those phases touch each other, what you'll see is that the liquid always comes in at a particular angle with respect to the solid. And that's called the contact angle. And the contact angle actually is different for, like the value of that contact angle will be different for different solid, liquid, vapor interfaces. So depending on what your fluid is and what the solid is that it's contacting, there'll be a different value for that. I won't go through a lot of the details, but if you ever go on to take a more advanced course, you can actually be shown that like the contact angle is related to the surface energy associated with each one of those interfaces. So far we've talked about how there's a surface energy associated with the liquid vapor interface, but there's also another surface energy associated with the solid liquid interface and the solid vapor interface, and those each have their own surface tension. Most times, like a solid vapor surface tension is basically meaningless because the solid is so strong that it never deforms, but you can still define such a thing, and it does exist. It turns out that the contact angle can actually be calculated from knowing those energetics. In practice, nobody actually does that. The contact angle is usually a measured thing rather than something that's calculated. So if you actually need to know what that contact angle is for an engineering application, you would usually the technique is you just create a little droplet, put it on top of the solid, like a very small droplet that's on top of the solid, and you take a picture of it from an angle and try to basically, you know, zoom in on it and fit the slope to figure out what the angle is. So in general, you never really have to worry about what that equation was. So just in general, anytime a liquid is very attracted to the solid, though, what you'll find is the contact angle is close to zero, meaning that basically, if given the chance, it will fully wet and form a continuous film across the solid. So that's like the ideal case of a liquid being extremely attracted to the solid. In the case of water, that would usually be called hydrophilic. That means that the water is drawn towards whatever the surface is and tries to spread out. Another word for that is wetting. So W-E-T-T-I-N-G. So some people will use the word wetting. A fluid wets a solid if it's attracted. The flip side of that is that there are a lot of, and for many applications, you actually want it so that the liquid is not attracted to the solid. So think of, you know, like water repellent, you know, outdoor gear. So in that case, you're looking for a solid angle that is greater than 90 degrees. And ideally, you can be up to 180 degrees if the droplet really doesn't want to touch the solid at all. In those cases, you know, like you basically have a freestanding ball of liquid that, especially if you tilt the thing at an angle, it'll tend to just roll right off. That's called hydrophobic, a hydrophobic surface. So and of course there's a whole continuum of possibilities in between. So for most things, you know, the contact angle is a finite number that is somewhere between 0 and 180 degrees. So for like water on a metal, typically the contact angle would be within like tens of degrees. On Teflon, it might be closer to 90 degrees, and if it's porous Teflon, it might be closer to 180 degrees. And so it really just depends on what the different things are. So just, you may have picked up on this, anybody who's good at Latin, but hydro means water. So hydrophilic and hydrophobic technically refer to just water, how water behaves when it's on top of a surface. But in practice, I think most engineers use all of those things interchangeably. So, when people say hydrophobic and hydrophilic, they don't necessarily just mean water. Some people who are, trying to sell their favorite surface will often emphasize words like omniphobic, which applies to more than just water. So a typical usage of that word is typically in the context of cell phones, right? So in cell phones, you've got oils all over your fingers, and often you don't want those oils to, get sucked onto the surface and leave fingerprint marks all over your devices. So like I think the Android sellers and Apple will often use the word omniphobic to describe the front screens of their phones.